Hello, I'm Guillaume Girol and I'm going to present you a comprehensive, automated and formal analysis of a family of protocol called noise. This is a good joint work with Lucca Hirschi, Ralf Sasse, Dennis Jackson, Cremers and David Basin. Let me first present the noise family of protocols. All noise protocols have in common that they establish a secure channel between two agents, Alice and Bob. Keys for encryption are derived from Alice's and Bob's asymmetric keys through a derivative of Diffie-Hellman key exchange. The important thing I'd like to mention about noise is the large number of noise protocols. The goal is that whatever your use case, you can find a noise protocol that fits. As an illustration, let me say that three popular systems that use noise, WireGuard, a VPN, Lightning, a layer of a Bitcoin, and WhatsApp, use three different noise protocols. More precisely, there are noise protocols where Alice has a long-term key and other where it's not required. Same applies for Bob. There are noise protocols which also take advantage of the fact that Alice knows Bob's long-term key and other which do not require that. I said that Alice and Bob have asymmetric keys, but it's even possible to additionally use a symmetric key if you have one. So assume that you want to use noise. You read the specification and discover more than 50 example protocols with widely different security guarantees. If you are not satisfied with them, you are even explained how to design your own. Given your own specific requirements and threat model, which one should you choose? This is the question we address. The thing is, verifying the security of one protocol is hard enough that you don't want to have to do so for like 50 protocols just to be able to compare them. For this reason, we will use an automated tool based on formal methods called the Tamarind Prover. It's a security verification tool at the symbolic level. This means that it assumes that cryptographic primitives work. The main reason for using Tamarind here is that it accurately models Diffie-Hellman operations, notably the fact that multiplication is associative and commutative. To compare noise protocols, we first have to determine their security guarantees. What this means is that for every noise protocol, security property, and threat model, we want to know whether it holds or not. Of course, we need to limit the scope. We chose the security properties mentioned in the noise specification, that is, first, secrecy, the fact that the adversary cannot learn what payload we sent or received, agreement, the fact that when Alice thinks she's talking to Bob, she's not actually talking to Charlie or even no one at all, and anonymity, the fact that the adversary cannot distinguish between Alice talking to Bob and Alice talking to Charlie. For threat models, we tried to be as generic as possible. We established a list of adversary capabilities specifying what the adversary can or cannot do. Can he be active or only passive? Can he impersonate Alice, impersonate Bob, or even the public key infrastructure as a whole? Can he compromise keys? There is one capability for each key: long-term, ephemeral, pre-shared, keys of Alice, keys of Bob's. We even distinguish between compromises before the session and other compromises. This list was established to allow us to model more advanced properties like key compromise impersonation resistance and perfect forward secrecy. The key element is that you can combine these capabilities freely with the AND and OR operators. This is what makes the framework expressive, but it also makes the number of threat models explode. For anonymity proof, which are considerably more computationally expensive, we had to reduce this list to limit the combinatorial explosion. But for other properties, that is secrecy and agreement, this amounts to more than 10 to the 12 threat models. As a result, we cannot just enumerate all properties and threat models, generate proof goals, and submit them to Tamarind. We need to be slightly smarter, which leads to our first contribution, a tool called Vacarme. There are two key ingredients in Vacarme to tackle the huge number of proof goals. First, some proof goals subsume each other. This means that without reducing the scope of the analysis, we can only prove some of them and soundly derive whether the other ones are true from the results. Then we can do some preprocessing. We designed a small and very incomplete prover inside Vacarme. It can do the easy proofs and lets us use Tamarin only for the harder proofs. Put together, here is a high-level summary of what Vacarme does. The input is any noise protocol. You have to specify it in the way prescribed by the noise specification. Vacarme parses the noise protocol and outputs a symbolic model for your protocol and a set of carefully selected proof goals. What I mean by carefully selected is that we cover more than 10 to the 12 thread models, but we only enumerate about 8,000 proof goals on average. Vacarme then runs Tamarin on these proof goals with a dedicated heuristic and collects the results in a nice human-readable table. In about 150 lines, it tells you what property holds in any of all the thread models I described before. Our second contribution is the insight obtained by running Vacarme on a number of noise protocols. Since there are infinitely many noise protocols, we had to choose. We analyzed the 53 examples found in the noise specifications. Some anonymity proofs timed out, but we still have interesting findings to share. First, the noise specification has a classification in levels of the security guarantees of a subset of noise protocols. For example, secrecy goes from level 0, no secrecy, to level 5, some sort of perfect forward secrecy. Those claims are informal and not proved. Prior work, a tool called Noise Explorer, proved that they are true, but we add that actually the description of these levels implicitly assume that ephemeral keys cannot be compromised. Also, the name of secrecy levels going from 0 to 5 suggests that they are monotonic, but that's actually not the case. In some threat models, I can use a level 3 protocol and be perfectly satisfied because I have secrecy, but if I upgrade to level 5 protocol, I lose secrecy. It's also interesting to know that in prior work, the informal description of security levels given in the specification has been translated by a human to a formal property before being verified. We don't need this step. Vacarme can automatically assign a formal meaning to levels because the levels actually correspond to equivalence classes of security guarantees. We also found interesting corner cases in the noise specification proper. This is a bit more technical, but for those of you who are more familiar with noise, here it is. First, about session identifiers. The specification does not mandate that the session identifiers are kept secret, but we show that if you leak a session identifier, then you lose anonymity. We also found that if you take a noise protocol which does not use a pre-shared key and add a dummy pre-shared key, then you can actually worsen security guarantees in a very non-intuitive way. But let's come back to our original question. I have two noise protocols, protocol A and protocol B, and I wonder which one I should choose. With our table of what property holds in what threat model, it should be rather easy. If for all properties on threat models, when it holds in protocol B, it also holds in protocol A, then A is better than B. Note that to be able to do that, we had to be very careful to formalize agreement in a way which doesn't depend on the protocol. It's not straightforward, but when you pay attention to this, you induce a partial order on noise protocols. You can see this order on the right of the screen. Arrows point to better protocols. Let's make it more concrete with an example. Let me zoom on the graph. To make sure we don't compare apples to oranges, assume that you want a noise protocol where both Alice and Bob have a long-term key, and Bob already knows Alice's long-term key. The noise specification has 4 examples of protocols matching these requirements. They are in green on the right. As you can see, KX, the top one, offers strictly better security guarantees as the 3 other ones. So in terms of security, you have no reason at all to use the 3 other ones, and we call them redundant. As a whole, we identified 20 redundant protocols. That's it. So I presented you Vacarme, an automated tool to determine the security guarantees of noise protocols that can compare them to choose the best ones. Note that the code of the tool is available as artifacts to the paper, and thanks for your attention.